It seems like I managed to, I have this distinct impression from last time that I managed to cast a pall over all of you during the course of the lecture. So by the end of the lecture, you're either starved or just generally, my most charitable reaction is that you were starved. Otherwise, you were not pleased with my numerous utterances during the hour and 15 minutes. So I'm starting off to put you in a pall right away by mentioning and bringing up the thinking ahead for the exam. So the exam's 2 weeks from now, and that's chapters 1 to 4. So it's chapters 1 to 3 plus chapter 4, which we're doing now. So it's sort of half this, the review for 2 weeks, and this is 3 weeks total, sort of. Pardon? No. Right here, or downstairs, or wherever we're going to be.
Are we ever going to be downstairs?
That's a good question. I would say we should just settle in here. Actually, for last semester, my office was next door. This would be, but it's not now. But the midterm's in class. It's Thursday. It's 2 hours, 11 to 1. All this stuff is posted already. It's been posted. So you should look at the web page if you want to know what's going on. Right? There's lecture notes, homework, the schedule. Everything's there. So. Yeah, last year's midterms there. So you should look at the web page. There's it's going to be like last year's. It's last year's posted solutions and things. So the information is there. This is also there, but I just wanted to emphasize that. Okay, because I thought that way I could depress you right at the beginning without wasting any time. Without wasting any time to getting to Markov chains. So. So I might the start might be if you are an old movie buff, meaning if you were watching movies I watched when I was your age, right? So you got to get in that mindset. Some of you are. So plastics, right? What does that mean? That's one word. What? Okay, what's the context, the trivia? Plastics. What is the context? Yeah, who said it? What? Yeah, good, The Graduate. Okay, that's the movie. Okay, and that's sort of, that's the one-word explanation about the key to success. I don't know, whatever, that... so it's a good movie. It's actually it's I don't know. I mean, maybe you think it's just a stupid movie, okay? But we thought it was a good movie. I don't know, 30, 40 years ago. I don't know. Geez, it's somewhere in there. It's quite a while ago. It's somebody well, you're already kind of past this. The age is sort of like maybe just starting college or something. But anyway, The Graduate. But the point is there's like one word summary of what you got to pay attention to. So I'm thinking about Markov chain. So I mean, how does that tie to this? Well, the analog would be, I mean, this is the whole thing, right? So I'm thinking, well, in a couple of formulas, what's the whole chapter 4? P and pi equals pi p. Then you think of that, then everything else can be understood as a refinement or variation of why, when this is not quite so, or there's more to say. But this is sort of the whole thing. So the model, when you're doing a Markov chain, the model is this matrix. And what you want to do is your model really tells you in your stochastic process how you move step by step. So this, in fact, tells you Pij, the entry of the matrix. So this is a matrix of elements Pij, n by n. N could be infinite. Pij is the probability of going from I to j in one step. So when we specify the one-step probabilities, and then we want to use the math to tell us the long-run probabilities, the probabilities of 4 steps, 2 steps, 100 steps, so forth. And in particular, we'd like to see something nice happen as the Markov chain goes through a number of steps. And in the long run, it'll settle down. There'll be some distribution about where it's going to be in the long run. That's this. So part of this, understanding at least what it's saying is part of will get you a long way. So in particular, this is a matrix, and these are interpreted as vectors, right? So this is n by n, this is 1 by n, this is 1 by n. So therefore, this is a row vector, this is a row vector, this is a matrix. So we're using linear algebra. But the general idea, if I wrote pi p without this equation, if I wrote pi p, this would be the shorthand. The thing we want to think of is, well, if I multiply two matrices, when I do so I'm now reviewing linear algebra not at the low level, right? So if this is m by n, then this thing has to be k by m, and these have to agree. Multiply two matrices. So if they don't have to be square, but whatever the rows here and the columns here have to match. So that's indeed the case here. And the final answer is then k by n. This and this. And this part goes away. And what you're doing when you do that, if you write, that's right, so we don't need this bad news anymore. Okay. Let's just remember that matrix multiplication, when we write, so B is a matrix, A is a matrix. So A is k by m, B is m by n. And what do we mean by the product? It's another matrix. And so we're going to say what its entry is, ijth entry. Well, it's going to be the sum of A I k, B k j on k. So when we multiply matrices, the elements, these agree, and the thing becomes k by n, and the ijth entry is this. And that's really, that's even when you take linear algebra, this issue is settled out by the first class. It's not the whole course, it's the first class. And all the rest of the stuff is much, much harder. But if you don't know this absolutely cold, you won't have any idea what's going on here. Okay? So I want to emphasize this point. So the meaning of this is just that. And so in particular, this itself is a matrix, but since it's 1 by n, it's another row vector. So when I do this, what's happening? This is a row vector. This is interpreted as the probability distribution. Where I am at some time, I have this distribution. And I transition according to p, and this is where I am one step later. So this is, if I start with a distribution pi p is what my probability distribution is one step later. So if I were to write this down, I would say something, well, the probability that xn plus 1 equals j is the probability that xn equals I, Pij summed on I. Well, this would be, say, pi I. So this would be the sum of pi I, Pij. That's this row, this thing, this would be pi p j. Pi pj would be just the probability of where I am at step n plus 1 given that I was pi was describing where I was at step n, and then Pij gives the transition probabilities. So this is the fundamental law of motion. So and it's just in linear algebra, all I'm saying whenever I multiply two matrices, here's how I do it. Here's what the entries of this matrix is. And this is the one thing that's absolutely fundamental. Everything else, and you use it all the time, and if you don't understand that, nothing will make any sense whatsoever. And if you do understand it, things should not be too bad. Okay. So actually, having tried, I'm now giving an exegesis of this thing here, right? Everything is this equation, but if you don't understand what it says, you're not going to appreciate the full implications. I mean, the plastics has behind it a huge story about why that's the hot thing to do, or was the hot thing to do. Okay. So what do we think of? We think of, so there's pi, just sort of thinking here's your space, and there's pi as some distribution on here, and then you do p, and you get a new thing, which is pi p. I mean, there's a probability law on here, and then you do p, and you get a new probability law. That's what this is here. Now let's think about what this is saying. This is saying that we now have an equation, and we actually want to solve for pi. So this is just a probability vector here, and this is a probability vector multiplied p, so this is another probability vector. So what this is saying is, I'm looking for a probability vector pi such that when I start with pi and I apply p, if my initial distribution is this, and I consider a transition one step, I get this. So I want to say that I have a certain distribution such that if I start with that distribution and I take one step, I still got that distribution again. It's very special. In other words, it's a stationary distribution. This thing is looking for a stationary distribution. This equation, see, it was first explaining pi p for any pi. But if pi is equal to pi p, that means the initial pi here is the same as the final pi here after I transform by p. That means that when I do this equation, if I write pi p j, that is by definition the sum of pi I pij on I. The probability of starting in I, and then given I started in I, this is the probability of going to j. So this is, now the left side is this. This is writing for all j. This is writing this matrix equation in terms of its elements. This is just rewriting that, right? And this is saying that the initial probability distribution is unchanged after taking one step. This is what I get one step later. Now, what you might imagine is, and this is indeed the sort of ideal situation, is that if you have a Markov chain, well, this is a distribution such that if you start with it, you stay there. So you might imagine a nice situation, which occurs in great generality, is the Markov chain, as it moves along, it converges to something. There's a probability distribution of where you are that's going to be fixed as you go for a long, long time. You're going to get closer and closer to this. And if you start with that limit, you'll stay there, because you're always going toward it. And if you start there, you stay there. And so the story would be that there would be some unique pi that's a stationary distribution where you go to in the long run. So the story you'd have is you'd take p to the n, and this would go to something we might denote like this. This is a little bit. Now, this is, I guess I should, this, I want to not confuse the number of elements with the, so k is going to infinity. And this is the steps. And this is the states. Right? There are n states in the state space, but this is the number of steps. I don't want to use the same. So as I take more steps, I raise this to the kth power. And what ought to happen is, no matter where I start, I'm going to go to some distribution, and this is going to be this pi. And so this is a matrix, so this is n by n, except all the rows are the same, because it doesn't matter where you start. So all the rows are the same, and they're all this pi, which satisfies this. And that's what ought to happen. In other words, as you go for a while, now this is where the numerics comes in that you do with MATLAB. You make some Markov chain, and you raise it to some power, and lo and behold, all the rows are the same. And you see for yourself. You see for yourself that if you start with some p, and you raise it to a power like the 10th power or the 20th power, the regularity you see is it's almost all the rows are almost the same. And so if you knew what that limit was, you'd sort of know what was going on. It would be the same. So the point is p to the 10, p to the 20, p to the 3,162, p to the 10 to the 6 plus 10 to the 4th. All of these, all of them, no matter what you looked at, would all look like this. That's the simple story. That's why you calculate this, because this tells most of the story. But you want to see it. So if they're calculating it, you sit there and compute powers of transition matrices and see for yourself that that's really what's going on. If you have a p, then you want to know what happens in the long run, you solve this. Okay, well, this isn't always so. So there's a lot of the rest of the stuff is exceptions to this story and variations of this story. So let's return to our example that we had before of Markov mouse, and where we have these doors. So you're moving around these rooms, and you go from 2, you go to each of the neighboring rooms when you move with equal probability, with probability 1/3. Now, this example actually has a lot of nice things about it. A really fantastic example that you could, for example, easily analyze in less than 30 seconds. You could analyze the 100 by 100 maze. That might surprise you, that you could do the whole thing. You could describe pi for the 100 by 100 maze instantly, but we'll come to that later. This also has the quality that, well, it's a nice small problem. That generalization is not obvious, but this small problem, you can figure out what happens in the long run just by thinking, right? So it's kind of worth, like you're taking SAT test or something. You get in that kind of mentality, you're going to figure it out, right? Or you're on a math Olympiad and you want to know, say this. Or you want to know this. So you say, what's the probability of going from 1 to 2 in 2,000 steps? Approximately. What's the probability of going from 1 to 2 in 2,001 steps? Approximately. I mean, this stuff should be, if you think of this should be easy. If you think right. I mean, but that's not any theory. I'm now just saying, well, you can be smart and see all this. You can see this. So the point is, this example actually has an exception built into this right away. Because the thing I think we talked about a little bit last time, but if you start in 1, say, you'll start in the 0th step, you're in 1. So in the first step, you're going to be either in 2 or 4. In the second step, you could be back in 1. But notice that every other step, you're in the odd states. And the corresponding other step, you're in the even state. So if you start in 1, you will go to an even state. And from an even state, you always go to an odd state. And from an odd state, you always go to an even state. So this is periodic. And the period is 2. The period is 2. This thing doesn't settle down. If you start in 1, the chance of, you're only going to be in 2 in odd steps. This is always 0. Because starting in 1, you can only be here, this is in the first step, you're here or here. So if x0 is equal to 1, then x2 will be an odd state, x4 will be an odd state, but the odd numbers you'll be in one of 2, 4, 6, or 8. So this will be 0. Now what about this sucker here? After 2001 steps, what's the chance of being here, given that we started here? Well, after all those steps, we're going to move around, and where we started doesn't matter, intuitively. Okay? So, however, we're in one of these states, because these are the even states, right? We're in the even states, but we're in one of these 4 in the long run. But we started in 1, but the fact that we started in 1 doesn't matter in the long run. We use that intuition. You know, you've got to do the test. You got to do it, and you got 5 seconds. You have 5 minutes to do the test. You're going to do it, and you're going to find the answer. So you see right away, well, it shouldn't matter where I start, and I got to be in one of these 4. And then you say, well, by symmetry, these 4 are the same. If it doesn't matter where I start, they're the same. So therefore, the answer here is this. And yeah, that's the right answer. Okay? Has to be by symmetry. These are going to be equally likely. I mean, it's obvious, right? If the initial state doesn't matter in the long run, then these are going to be the same. Then once you know the probability of being in all these even states, you can then just directly compute the probability of being in the corresponding odd states in the next step. So you could see that you would do now, the point is, this will be, in the odd states, this will be 1/6, and this will be 1/3. And you'll see that from doing calculations. You have to do a little bit of work, but you'll see that. So you'll see this is 1/6, 1/6, 1/6, 1/6, 1/3. And you'll figure that out by knowing that these are all a 4th, and just doing a 1-step transition from all of these. So from here, you see, if you were here, it's a half to this and half to this. And then if you're here, it's half to this to half to this. And you add all those up, you're going to get this. So you get this right away. So it's totally reasonable that you could solve this problem in a few minutes without knowing any theory, right? I mean, kind of one point of view is sometimes the problem, you can figure it all out if you just think about it. Just think about it a little bit. That the long run. Now, this is not equal. This is equal. This is going to be, cold 0. No, not 0.00001, but 0. But this is not going to be exact. This is only going to be, exact to, I don't know, this is pretty big. This is only going to be exact to a few hundred digits. Even this. So let's change it. Doesn't have to be so big. You don't have to go 2,000 steps for it to be nearly close. The amazing thing is you could go 20 steps. And then it's going to be exact. And this is where you just do MATLAB and you just say, okay, I make this matrix in MATLAB. That's the homework assignment. I compute this matrix, the 21st power and the 20th power, and I look at the entries. Okay, maybe this is 0.2500001 or something. I mean, when you look at it, it's totally obvious that for all practical purposes, the pi equals pi p answer is the truth, even though it's not exact. It's like the normal approximation of the binomial. This long-run thing, this solution, is amazingly powerful. So that's why you spend time learning about that. Okay. We got it. This mouse, we got to do more with this mouse. Well, let's just finish the obvious thing. I mean, so if you're thinking you want to do pi equals pi p, but if it's, suppose it's periodic. Well, there's two cases. There's the aperiodic and the periodic. The aperiodic is just this. I should use this again, 2 pi. Right? But the periodic case isn't that because it's oscillating. But the obvious thing here is if it's periodic d, you could write p to the kd plus p to the kd plus 1 plus p to the kd plus d minus 1 over d, and that will go to, right? If I take the average of all of the successive powers, so in the case of period 2, in the case of period 2, I would look at this. I'd look at the average of 2 successive ones. And then this thing will actually, if I do this, so this is actually going to converge. So the periodic case, you see, you don't actually have this because it's oscillating. But if you just take the average of successive, period 2, just take the average, it will converge. Now the way to see that is to, in this picture, let's think about what's happening. If you have the states are sort of, in our case, there's the even and the odd, and you're always moving this way. If you're here, the next time you're going to be here, and if you're here, you're moving here. And so you want to make a stationary distribution. You want to solve pi equals pi p. What would you do if you want this to have a stationary distribution here? You would put a half probability here and a half here, because you have to do this. You're going back and forth. So the stationary distribution would put a half here and a half here, and then that's corresponding to, then you're thinking what happens in the long run. So you're really having the pi, your 1/2 p, say 1, well, at any rate, you're thinking of this case where you put, in order to get this stationary distribution, you've got to start equally likely in the 2 places, because you want it to be balanced in the long run. And if you started with p here, you would always have probability p of being here in the even steps, and whatever. You couldn't balance. You couldn't be stable ever, because it would always oscillate. So you have to have a half here, and that averaging is the same thing that's going on in the averaging of the convergence. Okay. So one flaw in the long run story that it's not just always this. It's not always is if this p is periodic, because then it oscillates. But there's a modification of the story. And if you sit down and think about it, you'll see that it makes total sense to you, the periodic case. But otherwise, if it's aperiodic, you're going to have this kind of story most of the time. That's this thing here. Okay, now there's another big case there's another case that pretty much summarizes the whole story, and that's if we sort of we come back here. I knew I shouldn't have erased it. So we have this problem, and we have Markov mouse yet again, and we in the consideration of the mouse and the mouse's well-being, we want to liberate the mouse and let the mouse out. So we make an escape, say. So there's all these doors here, but we add a door here so the mouse can get out. And once the mouse gets out, the mouse stays out. Okay? So we make escaping Markov mouse. We have one more state. Instead of 9 states, we have a 10th state outside. So we make a new p. The probability of p state 10 to 10 is 1. And the probability of p10j is 0 for 1 less than j less than 9, right? So once you get to state 10, you stay there, and you don't go back. Okay, now when you say, now the point is, this is kind of a different situation, and the questions differ. You don't want to ask. The situation's fundamentally different. Because here, when you say, what happens in the long run? The long run, the mouse is eventually going to escape. Okay, there's some mathematics there, but you could prove it, but it's obvious, right? You're going to move around, and every now and then you'll get to room 3. And whenever you're in room 3, there's some constant probability 1/3 you're going to leave. And you're going to have that opportunity until you finally do leave. So the probability of eventually leaving is 1. So in the long run, you're out. The mouse is out. So this pi equals pi p doesn't serve much purpose because you don't care anymore. You know the long run. The long run is no longer interesting. The question isn't interesting. Once you made it so he can get out, you have a problem that changes your focus of attention. There is no interest in knowing the long run distribution. The long run, he will be in state 10 with probability 1. Okay, that means you want to know something else. The point is the questions change. So you're in a different problem. This is absorbing Markov chains. And the questions are different because now you're going to get absorbed. So so the questions that come up have something to do with what you can solve. But the questions are different. At any rate, let's think about the questions. Actually, it's a little oddness, but the oddness between what we focus on is what for which there's a story. So you could think of your own questions, and maybe this is some of them. But the question might be, well, if I'm starting in state 1, what's the expected number of times before I get absorbed? How long will it be before I get absorbed? And if I start in 1 and I know I'm going to get absorbed, how often will I spend, if I start here, how many times will I spend in 5 before I leave? These are the kind of issues, right? Okay. Now, suppose we wanted to, in this problem, suppose we wanted to find the expected time to get out. So you should recognize that as being similar to the problem we talked about in the book, about being stuck in this stupid problem about being stuck in the mine, and there were 3 doors, and one door you got out immediately, and then the other 2 doors you kind of went around again and came back to where you started. Right? That problem we talked about. This is similar. If you're here and you pick this door, you're out immediately. But if you pick one of the other doors, you're going to do something until you come back here, and then you might get to do this again. So the point is, what was the idea before? The idea was that you could find out what you wanted by solving a system of equations, by solving an equation, a single equation. But here, we can find out what we want by solving a system of equations. So let's suppose we let ETI be the expected time to get out from room I. So this is going to be 1 for each of the rooms inside, right? So there are 9 rooms inside. And we can then start to write these all down. So let's just write down the expected time to get out, number of steps. Time is number of steps. So from 3, we see it's 1 with probability 1/3. Because if we're in 3, we get out with probability 1/3 in 1 step. So it's always going to be 1. So maybe if I put this 1 plus, we take 1 step. With probability 1/3, it's 0 more because we get out right away. With probability 1/3, it's the expected number of steps from wherever we go to 2. And from probability 1/3, it's the expected number of steps from 5. Right? And so there's a number here, but you have an equation where it's saying, if I start here, it's going to take 1 step, so it's 1. With probability 1/3, I get out. With probability 1/3, I go to, 2. From 3, I go to 2 and 6. 2 and 6. Right? Okay, because I'm sitting here in 3, room 3, I either just one way out. Maybe that's causing confusion. There's one way out, and so it's 1/3 to each of these. And with 1/3 I leave, with 1/3 I go to 6, and with 1/3 I go to 2. And in each of these rooms I can set up a similar equation. I mean, it'll be one step plus wherever I go. So you end up with 9 equations and 9 unknowns. For each room there'll be an equation, and there'll be 9 unknowns. Okay, so you could you could figure out how to find out. That would tell you from each room the expected time to get out. Yeah.
Why instead of the 1 plus 1/3 times 0, why isn't it just 1/3 times 1?
Yeah, I'm saying you're going to take one step, and then given the step, this is the additional steps it's going to take. So you take, no matter what, you take one step. And then with 1/3 you've left, so there's no more. And with 1/3 you've gone to room 2, and this is the number of steps. And with 1/3, this is that interpretation that you will take one step. And if you get out, there's no more. And if you go to room 2, this is what's left. And if you go to room 6, this is what's left. Okay? I don't know. When I had 5 there, that could disturb you. Or if I had an extra door here, it could disturb you. There's nothing crazy in the arithmetic. So you can say, you could feel free to put, if I do something stupid, it would be good to correct me. So you'll help somebody, even if it's trivial. Yeah.
Same then as 1/3 times 1 plus 1/3 times 1 plus.
Yeah. This would have been the same thing if you wrote 1/3 as 1 plus 0, 1, plus 1/3 1 plus ET2, plus 1/3 1 plus ET6. Absolutely, right? That looks that way. Either way, that's either way you look at it, right? Absolutely, same thing. Yeah, maybe that's more natural. You think of 1/3 what happens, the probabilities, and then add them. This is actually, I guess, this is actually more natural. And the fact that I wrote this step maybe is confusing, because this, even though they're the same thing, it's confused. This is more straightforward. Yeah, I agree. I mean, you could say, all the difference is, you could say, I'm going to take a step no matter what, and then what? Or, I'm going to take one of 3 steps, and this is sort of, I think this is sort of more natural, but they're equivalent. This is again sort of a little bit how you'd think about it cleverly. So there's, it can get more complicated. And then then you sort of wanting some theory. So the complication comes when we do this. So now we make three doors out. And we call this state 10, this state 11, and this state 12. So I've changed the model, and this is getting a little bit more complicated. So somewhere here, you're going to want some systematic theory, systematic methods that will make life simple. So here's the mouse moving around, but the mouse can escape as before, but now it can escape from each of 3 doors. Same rules. So from 3, it chooses now one of the 3 doors with probability 1/3. From 7, it chooses one of its 3 doors with probability 1/3, and the same from 9. So from 3, and now you want to know, let's say you're interested in which door the mouse leaves from. So now you're kind of paying attention. What's the probability the mouse will leave from this door? And that means he's going to get absorbed in state 10, as opposed to leaving from this door and getting absorbed in state 11. So I've added 3 states, one for each of the places he can go out. So now it's 9 by 9, it's 12 by 12. I can have, and this probability of P 10, 10 is 1, and P 11, 11 is 1, and so forth, right? Because once I'm in state 10, I don't leave. And once I'm in state 11, I don't leave. And once I'm in state 12, I don't leave, right? So I've got 12 states now. Yeah.
Again, with the P to the N, because N gets really big, you can just see what the probability.
Yeah. So when you did, in principle, yes. So that's right. So you can see, in a way, you can see everything by looking at P to the N. And if you do P to the N, if you do to the P to the N, the trick is, the probability is, if you raise P to the N here, you will see that, you'll see right away, P to the N, you'll see the answer to, which, starting in state 1, if you do P to the 2000, and then look at the 110 entry, right? This will be the probability at this 2000 step, that starting in 1, that you're in 10. And it's going to accumulate, because you're going to be in the long run, there's going to be some probability of these 3, and that's all that's left. So you're absolutely right. Almost everything is just the matrix power. Now what's a little more tricky is if you said the expected time, the expected number of steps I took to get here. Now I've got to kind of look at all the powers. And that's where there's a little help. Right, to a large extent, everything is just looking at powers of P. And that's, and you could think it all numerically. Yeah, Michael?
If you leave and don't come back, doesn't that probability rise? Or it approaches 1/3?
Yeah. Well, if starting here, it's probably more likely to go out here than here. So these two are these two are equally likely by symmetry, but this is less likely, so they won't be 1/3. Yeah, and as you do higher and higher powers, the total probabilities of these 3 states is going to go to 1. Because just as before, in the long run, you will leave. And once you leave, you're stuck. And so these things are going to approach, and when you did you don't need this high, some fairly modest number like 20 or 40, and you're going to find that you've almost surely absorbed. So as I said before, and as you will be experiencing as you're doing this homework, that it remains the case that there's a certain basic theory which I'm trying to impart, but once you know that theory, the complication is mostly to find the right P, because that's the model, right? And you read this problem and you got to think about the P. And well, that'll be, if you have problems, that'll be discussed, and there's some of them are kind of tricky, so that will be, the homework problems we'll be discussing on, that Ieorertsj will talk about on Tuesday. Well, what I want to talk about in it now is, well, there's two, okay, the one part of the problem is how to analyze this systematically. And in the case of, this is the absorbing chain, but there are more than one absorbing state. So there's it's kind of interesting. And this story would still apply, though. You could still do this if you want to know the expected time to get out, all this story would be the same. You could do the same thing here. So to some extent, the model is P, and to some extent, what happens over time and many steps is there's powers of P. So the rest of the story then is, well, given that, is there anything else I have to tell you, right? That seems like the whole thing is right there, and there's not much. So there is some theory, and there's lots of books on Markov chains, so there really is a lot more theory, but to some extent, you've got to really absorb this basic stuff and really have it clear in your mind, but there is some theory. So here there is some theory, and I guess let's talk about that. So if I do this, I'm going to define Nij as the expected number of steps spent in J starting in I. mi, which is sum of nij on j, is the expected number of steps until absorbed, and bij is the probability of, let me call this k, just a probability of being absorbed in k starting in I. Now, as we discussed, this was, if I want to know the probability of being absorbed in k starting in I can just, I'm starting in I just look at the nth power for big N, and I look at this entry, right? And that's the probability I'll be there in the long run. So this is easy by powers. Okay, so these are the questions. These questions are here not because these questions are necessarily the only ones you'd want to look at, but because they're nice, simple answers. And the simple answers all have, the answers all involve linear algebra. So what we want to do is not even do this. Not even do this. We just want the answer to be, to calculate, well, these are all, the n is a matrix, it's got ij, and the m is a vector, and the b is a matrix. So we want to calculate those three matrices, and the high-level thought is we can calculate them by simply doing linear algebra, without even looking, and that may be, in some sense, even more simpler than this. Okay. So let me sort of, to do the linear algebra, I want to write P in a certain form. Now, this might be n by n, and this might be m by n. Now, this is the absorbing transient. So I'm rearranging the states. I'm labeling things so that the absorbing states are up here, and the transient states, the states I'm going to leave eventually, are here. So in our case, if I did this again, I would have, in our case, it would look something like this. I would have 10, 11, 12, 10, 11, 12, and this would look like this. And then I would have 1, 2, blah, 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 to 9, 1, 2, blah, 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 to 9. For the Markov mouse, I would have put the absorbing states up here, which are these three states that you go to when you leave, and then that's all ones on the diagonal, zeros off, and then zeros here. And then whatever is left, and this down here is 9 by 3, and this is 9 by 9. Right? And this whole thing is 12 by 12. This is the Markov mouse just in a picture. I've rearranged it so I put the absorbing states here, the transient, the states I'm going to leave here, and I put the entries in here. And so necessarily this is an identity matrix here. The whole thing is 12 by 12, but this, yes. Yes, thank you. Yeah, yeah. This is moving around in the 9 rooms. And this is going from the 9 rooms in one step to the out. And this is, once you're out, you just stay there. So this is this. And so in general, it has this structure where this is an identity matrix, and this is some sort of matrix, and these are some sort of matrices where this is, say, if it's n, this is m, and this is k, and m plus k is n. So this is m by k, k by k, and so forth, right? All these block matrices. Just divide the matrices like that. So this is a kind of canonical form that you want to do. It's a special case, but this is a canonical form for an absorbing matrix. You can put all the absorbing states up here, so you have this identity, this general form. So it's a canonical form. Canonical form for absorbing Markov chain. So this identity matrix, this is all these absorbing states, and then the rest of this. So without loss of generality, I could have taken whatever I wrote P first and put it in this form, just by relabeling the states. Okay, this is just a relabeling. And then what I want to do is just actually compute these things in terms of these matrices and just write it down and see what we get. So I want to say, well, what is the expected number of steps spent in J starting in I, and just compute it and see what I get. So if I do this and I say Nij, what is it? So I'm going to write down an expression for the expected number of steps spent in J. Now I'm thinking of I and J as both being in here, in these transient states. Because this is the expected number of steps spent in J starting, and this is the one where I'm here. So I'm moving around in these transient states, and I may visit, starting in I, which is a transient state, I may visit another transient state several times before I'm finally absorbed. And I want to know the expected number. So if the I is equal to J, this could be 1. So this is actually, if I count where I start, this could be Ij, which means that this is 1 if I and J are equal, if I count where I start, and 0 otherwise. But then I take one step. Now I'm going to write this down and see if this is going to make you happy or not. I don't know. So how am I computing this expected number? I'm actually looking at where I am after n steps. So in one step, this is the probability I'm in J after one step, and I'm counting that as 1. This is the probability I'm in there after 2 steps, and I'm adding that in there. So I'm finding the expected number of visits by finding the probability I'm there at each step and just adding those up. So this is the probability in 0 steps, in 1 steps, 2 steps, in n steps. And if I add all that up, I have the expected number of times I'm in J. It's just this sum going out forever. And when I should have this, because in the long run, I'm going to be absorbed, and these are both transient states. Now, there's 2 steps. This step is 1. The second step is the linear algebra. So it's unclear where the problem is. This could be a problem that you might not see, that the expected number of steps to go from I to J is this sum. The other problem is, well, what does this mean? What have we written down here? If we wrote it in matrices, we would have written this. Okay, this is the matrix version of this thing here. Now, what you ought to see is that's this. Okay, this is from linear algebra. Now, how would you see that? I guess you would say, suppose I multiplied by I minus q here. What's that going to equal? If I consider I minus q times n, then when I do I minus q times this, I get I minus sort of q to the n for a big N. If I stop someplace. Right? I stop, but it keeps going. I just stop here. If I do I minus q times this cancels. All these terms cancel, right? Except for the first one and the last one. Well, I guess I get qn plus 1. right? Because if I multiply this by I minus q for a fixed number of them, I'll have I, they all cancel except the first one and the last one. The last one will have an extra power, right? And this goes to 0, so this goes to I, because these powers go to 0. So the product of these two matrices is the identity matrix, which means that it's non-singular. This is a linear algebra, so they're non-singular, and then this is the inverse of that, and therefore this. Okay? So this is, again, a little bit more linear algebra. Now you're just saying, oh, when I do this expected number, it's this sum, and that's one thing you want to know. Then you write it in matrix form like this, and you recognize that this really is simply, this big sum is simply this. And so it's, if you want to calculate n, it's just this, just I minus q inverse. So you do this. So when you look on in the MATLAB program, it's going to ask you to calculate n. And the program is going to, you're going to insert q, but the program does this computation, just does the inverse. Yeah. Because we're only working within the transient states, right? This is very much within the transient states, and the transient states have the property that these matrices go to 0, because eventually you're going to leave there. So this division, this partition is very important, because what I'm doing is operating within these separate matrices, within this structure, right? So we're not just thinking P. We could deduce a lot of things from P alone, just its power, but now we're using these matrices, well, in particular, these two. So when you have an absorbing Markov chain problem, what will be the data? You don't need any data for this. The data are these two matrices. Input Q and R, and you're ready to calculate things. Well, we haven't used R yet, but Q is just this part. Okay, let's see. So now I want to go on to, well, this is easy enough. The M is where the M is just the sum of the over the n, right? So this is the n times a vector of 1s, right? We're just adding up the row sums in n to get M, right? That's row I, column j. So we're adding up over the columns j for the fixed row, right? To find out where, that's what this says. So once we've got n, M is immediate. And that's just summing up. This just does that. When you write multiply by a vector of 1s, it's doing exactly that. So this to a large extent, there's two issues going on here that got to be merged. One is that you understand the definitions of the quantities and why the formulas are the way they are. That's the probability. I mean, why is this the expected value? Then the other half is linear algebra. Why is this is writing, this is just means this, and that becomes that, and that's the linear algebra, which is just basic linear algebra, right? There's two pieces. There's basic probability to interpretation, and there's linear algebra. And those are two separate issues, but if you need to know them both. And this is not like the heavy-duty linear algebra, right? We're not going to have any heavy theorems here. Okay, so let's go to probability of being absorbed in the state. Now, this is transient, and this is absorbing. Obviously, the probability of being going in the long run of being absorbed in a transient state is 0. So now we're actually going from these states to these. So we're sort of doing, in one step, it's R. Okay, so let's write this down. Here, I guess, is okay. We've got this in mind. It would be nice if this board worked. I mean, it sort of works, but I'm not in, this is bad. I don't know, I'm not in shape to move this board up and down. It's stuck badly. I don't want to, okay, so now we want to do BIK. So we're thinking of the probability of starting some I here and being absorbed in an absorbing state here, but in any number of steps. So you can't be absorbed in 0 steps because you're starting here and going here. It's not the same place. But you could be absorbed in 1 step, right? In 1 step, it would be R, I, K. In 1 step would be that probability of starting would be this matrix. The ikth entry of this matrix would be the probability of being absorbed in 1 step. Because this part is the going from the transient to the absorbing is this matrix. But that's just in 1 step. So what happens in 2 steps? Well, in 2 steps, what can happen is we can move around here once and then get absorbed in 1 step. So in 2 steps, we get this. One step, we move around inside the transient states, and 1 step, we get absorbed. When we go in the next step, we get q squared r ik plus q cubed r. This is, and so forth. This is saying we take 3 steps in the transient states, and then we get absorbed in 1. Yeah?
One quick question again about the Q. If you were to do this with P, wouldn't you get the same answer then?
Yeah, because if you label things right, the P, part of P you're talking about is Q. I mean, you're just not going to be you're going to be computing from this part of P, because Q really is, I mean, this is P, and P is, if you use the right part of P, this part of P that you're talking about is Q. I mean, this Q and R are part of P. If you use the right part of P, it all depends on P. I'm just relabeling things about P. It all depends on P, but P is written this way to emphasize what it depends on. What part of P does it depend on? That's all I'm emphasizing. Surely everything depends on P, high-level thought. Yeah. Yeah, you have a problem, yeah. So if you use the whole thing and you start to do these operations, P to the n, this part won't go to 0. So if you just plug in P, the formulas aren't the same. But it's true that it's using, if you use the right part of P, which is precisely this part, if you do the same thing, so when you say this, but that's not true, because the absorbing states are going to not go to 0. You're going to have this, if the high powers of P is going to look like this. The high powers of P is going to look like this. This part's going to go to 0, but this part and this aren't. Right? P to the n looks approximately like this, right? If we start in the transient state, we're going to probability of being there is 0. This is where we get absorbed. Starting here, you can't leave, and so you stay there. So the large power of P is this, so you can't say quite the same things, but, right? Okay. So again, this requires some reflection, and the notes will be there, and you want to understand this. You might not understand this now, so there's 2 ways to interpret this. Just like any of these classes. One way is you see it, it's either totally obvious now, which is great, or you know what you want to think about, and it'll be in the notes. Okay? And so you'll think about it and understand why this is the correct formula from a probability point of view. Then now we're turning linear algebra. And you now say, well, what is this? But this thing is nothing plus this. If I rearrange the terms in matrix form. Let me write it first in matrix form. I'm seeing R plus QR. So if I wrote B is R plus QR plus Q squared R plus Q cubed R plus Q fourth R, so forth. I wrote it in matrix form. And then if I rewrote it again, I would have I plus Q squared plus Q cubed, so forth, times R, because all the terms look like that. And therefore, this is just NR. Right? So the interpretation problem is, why is this the right thing? Given this is the matrix form of that, and that's just rewritten this way, and so therefore you right away see that you've got this. So from the same matrix N, you can combine the N, which was I minus Q inverse R. This is the N we before, and we just do this. the high-level story again is the model's the matrix, right? The model's the matrix, so we got a P. I'm now saying, well, okay, for this absorbing matrix, I'm going to pay attention to the structure of P, and I have these two submatrices, R and Q. So the model becomes these two matrices. Then I'm thinking, okay, everything that I want to calculate are just linear algebra from that. And the pi equals pi p is linear algebra. That's solving a system of equations. Everything is linear algebra. Raising the power is linear algebra. So everything, the theory that's sitting there, to a large extent, I mean, we got finite state space, so we got finite matrices, but the theory to a large extent is linear algebra after you translate what it should be. Now, this particular take on the stuff is different from Ross. He doesn't really, he does this some places, but he's not, so you'll find that my notes on this are different. I mean, I think it's a good perspective. I'm trying to take the point of view that you know linear algebra, and if you don't remember it, you should. And therefore, it's worthwhile. Rather than saying that you don't want to know linear algebra, and therefore you shouldn't bother with linear algebra, and that will be an impediment. For sure, what I'm saying is going to be confusing if your linear algebra is not sharp. Not the deep stuff, just the real basics. But it will be worthwhile for you to use this as an opportunity to review linear algebra. You don't have to do a whole lot. I mean, the question of solving a system of equations, inverting a matrix, understanding that matrix product, those things are very basic. It's not hard stuff, but that all comes to play here, and there's other things as well. Okay, so we're. Is there any discussion, sort of general thought, major discussion that begins to emerge at this point is lunch, but okay, let's see. So let me just say a little bit here in summary. Let me try to say something about the story here, and then I'll come to one point that I'll come to later. So actually, here you have Markov chains, and you have ergodic. So I'll use this term, absorbing, and then you have periodic, aperiodic. Now, the nice case is the aperiodic ergodic. That's pi equals pi p. This is the general meaning of this is there's the state space, and you move around everywhere in here, and you don't get stuck anywhere, and you want to solve pi equals pi p. So this is recurrent, is irreducible. There's a bunch of words which we'll talk about, but irreducible, ergodic, you get this thing. Absorbing is certainly not irreducible, so you have this. This is where you have the n equals I minus q inverse, and the b equals nr, and so forth. Now, this is a big overview is, well, there are more complicated Markov chains. They could be more complicated than these, but they usually don't happen. They're usually artificial. Almost all problems are either this or this. And so the point is, this is really, this is a high-level view that you should take when you're reading this stuff. There is a theory here. It's not too complicated, but one dividing point is that Markov chains either are this irreducible kind where you keep moving around and there's going to be a steady-state distribution, a stationary distribution that you solve by solving pi equals pi p, or you have an absorbing problem. This is a major impediment because if you get messed up, if you don't realize there's two kinds of problems. There's the kind where you solve pi equals pi p, no absorption, and there's the absorption problem, ergodic and absorbing. So you're sort of, if you're thinking of if you were doing a test and you read the problem, if this stuff is shaky, you'll read this problem and do pi equals pi p, because you're just sort of like you're a machine, and you say Markov chain pi equals pi p. It's this problem, but it's not this one. So that's not the thing to do, and you just get messed up. You need to see at a high level there are two types of problems. One's this kind, one's this. They got different questions, different theory that supports it. And that big picture will really help. So when you look at the chapter, you're going to be learning about these through the course of the chapter, the absorbing problems and the pi equals pi p problems. And over here, there's a slight division about periodic and aperiodic. If it's aperiodic, it's very simple. You just go to the thing. If it's periodic, you're going to oscillate, but it's going to still have the same character. So the story really, what I'm trying to convey in this class and the last class is a kind of simple picture of the whole story. That there's a few basic problems, and each of them can be solved with linear algebra. And the MATLAB homework contains examples of the Markov mouse, the escaping Markov mouse, with the data, with the programs. So you don't need to do anything except just do it, run the stuff and see it. But you could do your own programs, to relearn your linear algebra, learn the program, remind how to do inverse and solve systems of equations. It would be good. That would be a good thing to do. You won't be tested on that here, but for your own feeling of confidence, you could be doing this linear algebra yourself. Okay, where are we? Thursday. So I'm collecting homework if you have it to offer. I think there was some of it. The old homework is going around. Mostly it came back on Tuesday, but